All right, welcome back. We are INFR3110. That's Game Engine Design and Implementation in the Fall 2020 semester at Ontario Tech. And it's week 2, part 1 of our broadcast. And today we're going to be talking about a few topics that make students go crazy. And I'm going to talk about that because they don't like talking about UML. They don't like talking about pseudocode or flowcharting or any of that stuff because it's documentation. It's the dreadful documentation. And, a lot of us don't want to do any of that stuff because it's tedious sometimes or it's ugly. And we'd just rather code or do art or design or something else. But I can tell you that this is part of the process. So let's see where we are right now. We're sitting here at week 2. September 18th. It's D&D night for me. I'm not sure about you, so I'm really excited about doing that tonight. I know we also kind of discussed last week a bunch of stuff. I gave you some examples from a object-oriented programming perspective of classes, monsters in D&D and stuff. So I'm going to continue to make some of those things only because this is just me. This is how I relate. So if it really bugs you, I'm sorry. I don't mean to bug you. But I'm going to try and make it so it's a little interesting. So we're going to be talking about UML, pseudocode, flowcharting, a bit of a comparison and analysis, and we're looking at features of game engines in general. So that's kind of what we're looking at from a game engine's perspective today. So it should be pretty light on the second half. The first half is heavier in terms of the content. One thing to note is that it says Group Assignment 1, Part 1 is listed here. This means that I would give it to you. That's what this means. And I guess I should have put like released and due as a column. This won't be due for a couple of weeks. I'm going to make it due probably or earliest next week as an example near the end. But I'm probably going to make it due a couple of weeks to get you guys going and give you guys a chance to get going on it. Group 1 Part 2 I'm going to host in 2 weeks from now live. And the reason for this is because we're going to have a checkpoint. So that's going to eat up a bit of time in our meeting. And then I'll give you Group Assignment 1, Part 2 to kind of do in class. And hopefully we can all finish it off as much as possible before the end of class. So that is Group Assignment 1, Part 2. Okay, so that's what's happening there. All right, so again, I think it's the topics we're going to cover today are quite detailed, and you can take them as deep as you want. I'm going to skim the surface of some and go deeper into others. So what did we do last week? Last week we kind of did a course intro for people who weren't here, and we talked about the course outline. We talked game engines, but a really high level. We also talked about coding best practices, version control, and OOP concepts. So if you haven't had a chance to look at those slides, again, they will be if I ever host anything like a quiz, which is also possible. Today I'm going to do a bonus in-class exercise that's coming up, which should be listed actually up online. It should be available for you to even start now if you wanted to. If you skip ahead and do what I'm asking you to do, you can finish and get your bonus marks, which are always good. Without actually waiting for me to tell you what to do, you can probably figure it out. Let's continue though. So this week what we're going to do is talk about software engineering, UML, flowcharts, pseudocode, and in the second half, game engines. So let's get into what is software engineering. Okay. So really, when we think about it, the software development lifecycle is really what we're talking about here. It's a systematic method where we do things like develop software iteratively using agile project management. I think agile project management best practices allow us to iterate. Like we talked agile at a very high level last week, but more or less what we want to do is we want to have a series of sprints, and each sprint, what we're going to be doing is the sprint is going towards a release, whatever that release is. We might have more than one sprint for each release, and let's think about sprints as a small body of work that we're going to do in 2 to 4 weeks. And we'll talk more about project management best practices and all that stuff down the line. Worst case, I may have our friend Nicholas go over some project management stuff with you in lab, but I'll see if I can cover it during lecture as well. So it can help you with the whole process. We're also going to have requirements when we do software engineering. One of them is this idea of a business requirements document. I'm talking about in any software engineering kind of outfit, and not just necessarily with game development. So what we do is we kind of create something called a BRD, which is a business requirements document. Back in the day, there was a split between project managers and business analysts, actually, And business analysts always manage this thing called the BRD, a business requirements document, which just listed all the requirements for that particular software project, whatever they were. We also use component-based architecture. So a lot of the times we use things like design patterns. We also plug in libraries. We also include things like frameworks, whether it's front-end framework, a back-end framework, database framework, all kinds of stuff. So we have different components that are part of our software engineering journey. And many times we model software visually, and we use visual tools like UML, like flowcharting, and like some tools that automatically translate. So when you actually do something with a visual tool, it writes the software for you. Some of the software anyway, some of the code. And we'll talk about that. Nick is going to show you how to do that in Visual Studio 2019. We also want to verify quality. So it's not just about good coding practice, but also about doing some quality assurance and testing. Okay, and sometimes it's a one thing. We also control change. So the IT service management best practices, and let's take a look at something called ITIL out there. And I want to talk about this because you may not have access to or have ever heard of it. So there is something called ITIL, right? And what it is IT service management. If you look it up on Wikipedia here, why not? We'll look it up on Wikipedia. But I know this is a wall of text for you when you're looking at it, but if you want to do some reading about it, what it is the IT infrastructure library, and what it does for us is it provides a series of IT management tools, things like change management, incident management, and so on. So it's a whole way of managing software and service. Okay, so this is all part of software engineering, and it's much larger than just doing game development. How about this? What is this? And this is something that you guys are going to be seeing down the line. Can anyone tell me really quickly on the chat? It's a class. Thank you. It is a class, but it's like a diagram of a class, right? And we're going to be talking about this in a second. This is UML, and we're going to get into UML right now. But it's broken down into these three sections. Can anyone tell me, before they skip, don't look ahead, see if you can remember, if you've already done this, what are the three sections that we're looking at when we look at a UML object like this? So what's the first section up here? What does that mean? Oh, there we go. Daniel says it's name, members, and functions. Absolutely, that's the way it goes. So I'm not sure if you saw that or if you know it. That's great. So name of the class goes up here when we draw it. The member variables are here, and the functions or methods or behaviors are in here. Okay. Also, they're called attributes or operations down in here. We'll talk about those things as we do our UML diagrams. Okay. So nothing to really be afraid of. It looks weird when you first look at it, but if I was to give you something like this, and I said, I want you to make this class, you should have an idea of what I want to make, right? So it doesn't take much longer to look at this. Look, I have a person, and the person has a name and an age. Actually, this is a classic example of the person class. So again, UML, what is it? It's called Unified Modeling Language. That's what it stands for. It's a pictorial language used to make software blueprints. That's definitely for sure. And it's described as general purpose because you can use it for other things, not just software development. You can also use it to describe relationships in software systems. So when we put a UML diagram together, what we want to do is to do some analysis. This is like before we even do the first bit of code. So if I'm thinking about stuff, let's say your lead software engineer brings the developers into a room and they start talking about creating an engine. We can certainly write an engine and just, spray and pray. That is a method, right? Just write and see what happens. Or we can be a little bit more, take a little bit more care and do some planning. And part of the planning is, hey, what are our classes going to look like? This is a great exercise. And one of the things I'm going to be asking you today is, can you describe what your engine looks like or what your game looks like from a UML perspective? That is the bonus exercise. So it can be done for everybody. So I'm looking at having you guys practice this, whether you're using UML, flowcharting, or pseudocode. We can describe one part of your engine. All right, so UML components, they're structural, behavioral different kinds of grouping components, annotational. We're going to be more focused on structural components because that's the kind of class that we're in. From a structural component perspective, we have different things. We have classes, we have interfaces, we have ways of collaborating. We can show collaboration between one class and another, and we can also show components which describe physical parts of a system. Okay, so that's a structural, kind of way of our analysis, if you will, of looking at a software system. So from a behavioral perspective, we want to describe the interaction between one class and another. Sometimes we also want to think about describing a state machine. And state machines, by the way, are very useful from artificial intelligence perspective to even scene management. We can also use it for animation management. We use a state machine in Unity and even in Unreal to kind of manage how to go from one animation to the next. So whether you're a designer, whether you're a programmer or an artist, state machines is something that you're going to start learning about if you're in game development, if you don't know about them already. When it comes to grouping, what we want to think about is it's a mechanism where we want to group elements of UML together, and usually we want to group things together because it makes sense. Like, so for example, this grouping is all part of one system. This is why we would group it together. From an annotational perspective, really what we want to think about is it's really remarks. Think about this as almost like I want to make labels to describe a system, and it has nothing to do with the UML models themselves, but actually outside of the UML models. Remarks, sticky notes, that kind of stuff. It's all annotational things that we want to add into the UML diagram. From a relational perspective, this relationship stuff is the stuff that you are going to think about. So there's 4 common types, I would say. There's more than this, but there's an association, and there's different kinds of associations, a generalization, a realization, and dependency. And when you look at these words, you're like, Tom, what do these words mean? How am I going to remember this on my final test? And the answer is it's going to come. Don't worry, we're going to talk about it. Okay, this is part of the exercise. What I'd like you to do now is grab staruml.io, go over there to staruml, download this for Windows. So what it looks like is if I was going to do it, if I go to staruml.io, okay, and if I was going to download staruml for Windows, we're doing this together. It is a little app. It's not free. There is a cost to it, but there is a trial that we're going to look at today. It takes a bit of time, so please, 127 megs. I don't think they're sitting on a crazy fast server, so it'll take some time to download. But the great thing about this is you can design classes, and it's perfectly compatible with what we're going to be doing today in today's in-class exercise. As well, from a documentation perspective, one of the things you're going to have to be doing for your group assignments, as well as for your project, your team project, we're going to be talking about using UML, Pseudocode, or flowcharting, and this tool isn't bad for doing all those things. So now that I've downloaded it, I'm going to set it up. Again, this is just a quick setup about how to do this. So if you missed today's class, then hopefully it will be useful to you. It says buy now, and for me, I'm going to evaluate. All right, so that's what I'm going to do, just like you. Okay, so what is this? What do we do, and how do we do it? Well, if you take a class here, I'm going to just show you. You can draw it out. So basically, you sit there, and now we have our 3 mechanisms, right, that we talked about before. So you can see here that I'm just going to zoom in. You can zoom in by pressing Control and using the scroll wheel here. And you can see that here the class is called class 1, not really that descriptive. What I'd like you to do is go down here to where it says properties and change the class to something else. Let's do that person class that we saw before. So person. Notice it changes the person class right there. It's pretty good, right? What we want to do with the person class also is on the right, you can see there's a model explorer. Now this doesn't matter whether you're using this tool or other tools, they're very similar when you look at them. But here what we want to do is if I right click, I can add a bunch of different things. Remember what we said, attributes or operations are the 2 things that we can add in there very simply. All right, so let's add in some attributes. So there's two attributes I want you to add. Try this. I want to add a name attribute and I want to add an age attribute. So let's add the attribute name. So here's our attribute name, except it doesn't say name, it says attribute. Let's go to the right here in the panel on the right in the editor and change this to name. And I want to change it so that, let's suppose that the attribute that we're talking about is a private attribute. So it's a private member. So we would call it M underscore as an example, which is a convention for member variable. And then name, lowercase, enter. There you go, M underscore name. Notice that there is this plus here. We're going to go into that in the actual PowerPoint as well. But I want you to change this from public. There's different kinds here. Public, protected, private, and package. Let's go to private. So now notice it becomes a minus. So minus denotes it's private. So whenever we see anything with a minus in here, and heck, even if we see the underscore, that should be a clear indicator for you that this is a private member variable. That's what it is, name. You can also specify the type if I want. For example, I know that my name is going to be string. I'm just going to put in string in there, and it'll actually put the type next to it. Okay, it doesn't have to be something that you define. In fact, you can make your own custom types, data types, if you want to describe this as well. So really straightforward. Right click again, let's add in an age attribute. So here's age. Again, it just gives me attribute 1. I'm going to go in there and change it to age. Okay, and it's also private. So let's rename that so it's proper, M underscore age. And we're going to make it private. And we're also going to make it the type, let's suppose, is an integer. Okay, you can also make it a float if you feel like you want to be that specific for people, that they might be 18.3 years old, as an example, or something like that. But my person is going to be whole numbers when it comes to ages. Okay, pretty cool. All right, I want to add in some a public getter or setter, and we're talking about when it comes to getter and setters. We can rethink that, or we can create another way of talking about getters and setters, which is we can use a get accessor or a set mutator. There's two types, right, of accessors, if you will, right? So a get accessor, a get method in C++ or even in C# starts with some kind of, usually we say get or set. Those are two things we use. In C++, it's that way. In C# it's not. In C# it's just a capital. Usually the convention, the name of the getter will be capital N, and you would have get set. So the way it would look is like this. I would right click, I would add, it'd be another attribute. Notice that there isn't property. That'd be awesome if there was something like that, property, but there isn't. Attribute is the proper name for it, attribute. The attribute is going to be called name, so capital N for name, and I want to make it public. So if I just press enter here, it's just going to say public name. But the right thing to do is next to it, I like to put in something that looks like this, get set. Okay, that's just me. So I can see that immediately it's got, the name has two parts, a getter and a setter. The getter connects to, I return M underscore name, and the setter sets underscore name, get set. You might also, in C++, we might call this get name, set name. It's up to you how you want to code this, but this is how you would see it as an example in a UML diagram. Let's do also the type. We can also have the type in there, and we know that the name, the type that we're returning typically is the same as the type of the member variable. So from an object-oriented perspective, remember that we want to use public properties, which is what this is, and private instance variables, or here, what this is. So private and then public. Public is the face, think about it as the ambassador of the private data member back in here. All right, so name. And so what I want to do with name then is I can do a couple things. I can talk stereotype, or when I say type, it's going to be, of course, a string. Okay. Right click, we're going to say add, we're going to attribute. You're probably ahead of me at this point. You know what I'm going to do. I'm going to call this age with the capital A, and we're going to make it public, but let's make it so that it's coded properly. Get set. Okay, this is typically how I do it, and the type is going to be int. Okay, and there we've described our attributes. Okay, our attributes. And then I want to make my operations or methods. You could also specify the person operation or method, which would be the constructor function. Okay, right click, We can add a new operation. All right, notice it automatically contains brackets, so guys, you don't have to include it. If I made an operation with the same name as my class, person, as an example, then you could see this as the default constructor for the person class. Okay, the default constructor. Why? There's no parameters, right? However, I could add other constructors in here as well. If, for example, let's suppose I wanted the person constructor, to have other parameters, I can add those in as well. Okay, so as you can see, it's not terrible. It's not terrible in terms of the way we go, right? And so here we have our properties, as you can see. By the way, up here, notice that we have a bunch of different things that are listed here in the outline. That's what this is really cool for, right? So that's one. And then what we want to do is, because it's public, what if I did something that, for example, I wanted to add in additional properties? How would I do that? So if I right-click here, as an example, and I want to add parameters, I can just go right-click parameter, right? And this parameter is separate. Notice it comes in separate. It's underneath, almost like a subsection of my my operation, which is my function. So this parameter I can specify, and I can say, well, guess what? I want to have age, lowercase age now, which is of type string. So that's the first thing I want it to take. And I also want to add in a parameter here. So when I say add parameter, notice I clicked on here to make that happen. And then in that parameter, I can specify, and I made a mistake. We're going to fix this in a second. Name, and we'll make that a string. And we can also move them around. Notice that you can kind of move name and age, right? Like there's name and age here, right? But on here, on the actual outline, right, what we want to do is we want to have age, as an example, be an integer. No problem. Let's do that. There's int and name. Okay, so that's pretty good, right? I mean, it's not too crazy. We can move it up. So we want name first and then age. So we can do that. All I did here was I click this, and where you can say I can move up or down. So pretty cool, right? And this is why I kind of format this way. So this is my person constructor. That's what this thing is. And then what I want to do is I also want to add in my one method that's slightly different than a person. Each person will be able to say hello. So we'll make a says hello method. So right click, add operation, and we'll say that this operation says hello. Again, you might decide to make the operation lowercase s if that is your convention. I'm going to make it uppercase for all my methods. Okay, especially so. Example, even my getters and setters are uppercase. My public methods are also uppercase. So says hello. So that may be something. And notice that says hello needs a return type. So I'm going to return void, right, which is what I want for this. So notice that there is no return type here. So I didn't say that there's any kind of return or anything like that. If I right click, notice I can add, and it says a template parameter, and a constraint and a tag. All right, so those are all the things you can do. You can also format. You can add additional things to make it look nice and so on. But for now, let's just leave it as my person and says hello, right? Which is pretty cool. So that is at a very high level what you can do. But what if I wanted, as an example, I'm just going to drag it around now. What if I wanted a subclass of my person class and I want to make a student? So if I double click, it's going to say a couple things here. I can, if I kind of go around here like this, you can see that there's these little icons, right? And one of them is this, add subclass. And there's also this, add superclass. So I can do both subclass and superclass, as well as provide an interface, right? Or add required interface, or add associated class, or add aggregated class, or add composited class. We'll talk about composited class later today, all right, and what that means, how we can use that. But definitely we want to add a subclass. Let's say if I was going to make a subclass called student, click that button, you're going to see that immediately I have a class with an arrow that points to this, right? And that arrow means inherits from. That's what that arrow means. Anything solid arrow like this with a big arrow inherits from, we can make our class just like before. So again, I can just double click in there and change the name. So we'll call this class the student class, right? And I want to add a couple of parameters for the student class. The student class is going to have a new attribute called student ID, and we'll make it a getter setter. I'm not going to go into details. If you wanted to go into more details than this, you're definitely welcome to do so. So an attribute which is including a getter and a setter. So this is a default property is what I'm saying here. So if I do this and I don't have member variables, that means that in C# especially, it's automatically generated for you. And there's a quick way of doing that in Unity, right? If you use the prop keyword, it'll actually generate a property. And that's what this is called in C# as opposed to C++. Nicholas is going to go through the nuances of C# versus C++ with you in the next week's tutorial. So that's pretty cool. All right, so that is student ID. Student ID is also of type string. So we're going to say that it returns string. My student is going to have a constructor function. So we're going to say that it has an operation also called student, right? And the student operation, as an example, it's going to have a couple things here. I need to add a parameter. And the first parameter is going to be the name parameter, because I want to have that same thing, name, which is of type string, because it has to satisfy, whenever you make a constructor of a subclass, the constructor of the subclass most often has to satisfy the constructor of the superclass, right? So therefore, that's the first thing. We also want to add another operation. By the way, this is only one way of doing it, another parameter. And the other parameter is going to be, and if I'm going too fast, forgive me, I just want to get through this, and then it's listed inside the PowerPoint. The other parameter that I want to add in here is age, right? So this is the same stuff that is above. So type is int. Hopefully you're coding along with me here. And then finally, we want to add another parameter which is specific to the student class. So I want to add a new parameter, and we're going to call this parameter student ID. So student. Sometimes from a convention perspective, when it's two words, we might do this, student ID. Sometimes people do this, student ID. I'm okay with either. I'm going to use this, underscore. So student ID. Student ID is also going to be of type string, because we're going to have a long stringy student ID. And so there you go. That's our student constructor function. Okay. We want one more thing. I want another method that is something else related to students. Let's make a method or an operation, and it's going to be returning void again. So there's nothing it's not going to take a parameter or anything like that. This method is going to it's going to be studies, or is studying. You can also say that too. So let's just say studies for now, just to keep it nice. So studies. It's also public, as you can see here. All of these things are public. And now we've kind of described a very simple relationship between person and student. So hopefully that kind of gave you a sense of how to use this. Now, how do we take this and use it as an example in our documentation if we're not paying for this thing? Well, you could always take a screenshot, right? So that's something that's nice. You can't save your stuff so easily, although if you go to File and you go Save, you could save it here. But a lot of the stuff that you can do here is restricted. And I think it's a great little tool. There's other ones out there as well that do very similar things. But this will be sufficient if you do something like this for your documentation for me in this course. Okay, so that's kind of the first thing. Could I show how do I make the initial class for the class? On the left, see where there's on the left you see class. If I actually click there, I can draw a class, right? I can do that just like that. And if I press delete, I can delete the class. So that's one way of doing it. I can also make an interface that way as well, and a bunch of other stuff in here too. Anything else that I want will be limited only to what this tool allows me to do. Okay, so that should help you out. Yeah, I know I was going a little faster, but the great thing is it's being recorded. So you'll be able to see this video later on, worst case scenario, if I went a little bit too fast for you. All right, so hopefully that gives you a sense of very simple diagrams here that we created for the person and student relationship, right? Again, I urge you to take a look. If I go right click, you can add, if I look at the actual object itself, I can add a class, an operation, a signal, a data type, an artifact, and there's a bunch of extra stuff that you can explore, state machine, all right, and so on. And try it out. Try adding some stuff out. Let's try adding some random stuff. Okay, so let's make another class. So again, I'm going to click on the class first, draw it. I don't care what this thing is. And then click away, right click, and see what happens when I add a whatever it's going to be, right? So try it out. Like it's a tool for you guys to explore right now is what I want you guys to do. So if I add something like a state machine, what does that look like? You know, as an example, here's my state machine. And if we call it something like, it says state machine 1, notice it doesn't really show up right now, but it does show my class 2 right here. And there's also class 1 that kind of didn't show up, and it's kind of gone, right? So that's something that is gone. And you can notice on the bottom right, there's a little mini map of what I'm looking at on the bottom right. I can also, again, zoom in with control and scroll wheel. I can also remove, I can delete from my model things that even whether they're shown or not, I can delete from my model. I can also make my model and drag and drop. So example, if I was to delete this thing here, and then if I just drag and drop into here, it'll add it in again. So these are all good things. Lots of control. Here's my state machine. It doesn't really show my state machine, and I can't really do anything with my state machine, but here I can show my state machine, and I can see that there is a region. I can talk, if I right click, I can add a constraint. I can add other things in my state machine, right, as an example. So lots and lots of stuff that you can do with this object. So state machine is not that visual. Let's go into other things too. Let's try one more or a couple of other things. Let's try a component, see what that looks like. So again, not really visible here in the diagram. How about other stuff? What about a template parameter? Okay, that's interesting. So we have a little template parameter there. And what about if I want to make a connection from one class to the other, so manually? So let's say I want to bring this class, and I'm just going to press down my mouse wheel to scroll, and I want to move this down in here. And by the way, you can always remove stuff here too. So if I don't want my template parameter, I just can delete it. So let's cut that out. Let's cut my component out. I don't want that. I'm going to fix this class up right here. No state machine. Bye-bye state machine. And now I want to make a connection between this class and this class manually. So I want to make some kind of an association, or you want to make a generalization, let's say between this class and this class. I want to make a generalization. How does that work? How do I make a connection, as an example, before that? So again, notice that there are different interactions that you can add in. So if I want to make a collaboration, you know, as an example there, I have a collaboration link, and then from there it'll do stuff, right? Let me just add diagram. It says a sequence diagram. That's pretty cool. An activity diagram, a state chart, a flow chart diagram. So you can add other things in here too, and a bunch of other things that we can explore. I'm not going to go too much into this. This is for you guys to explore how to use this tool, and Nick is going to go through a lot of details about how to do UML diagrams with you. For now, let's suffice to say that we can do a lot with what we have here in Star UML for free. Let's get back to our PowerPoint presentation. Now we'll keep this thing open because I'm going to go back to it. All right, so we have, if we screenshot this, it would be sufficient for bonus? Absolutely. Thank you. What if you don't have a game plan yet? Do we just do random code diagram? Well, why don't you code what your game object would look like, as a good example, Roderick, or try and think about what a game object would look like and what other object. If you were going to code your own game engine, what would your game engine objects, how would they look like? How would you code them, you know, as an example? And imagine if you were going to create a game object hierarchy using object-oriented programming, which may not be what you want to do. Maybe you want to use an ECS, but let's suppose we're using an object-oriented programming hierarchy. How would you code that? How would you use that or show that in UML? So that's UML. Why UML? Because again, a lot of things, you're going to have a lot of different users that take a look at your code. There might be business people, analysts, coders, testers, designers, and they really want to understand how your code works. And actually looking at code, some people will not understand what that means. But looking at a diagram, you know what they say, a picture is 1,000 words, right? It speaks to you. So that's the reason why we do UML in many ways, especially when we're looking at a diagram together at a very high level before there's any code, and you're designing. You're actually a designer from a coding perspective. You're designing your code. You're an analyst, right? And you're going, well, does it make sense that we have this kind of class connect with this kind of class over here? Does it make sense? Wouldn't there be duplication, or could we not use code reuse here if we had this class, this abstract superclass over here? That kind of stuff. So those are the kind of conversations you can have by using things pictorially. All right, what is a use case? A use case, you're going to hear about this, represents some kind of functionality of the system. A lot of times what we want to do, we're going to talk more about use cases in future lectures, but really what we want to talk about is we say, so if I want to describe a use case, I want to walk a user through, using a system. That's what a use case is. It kind of represents the functionality, how a system works, right? And we want to use tools like UML or flowcharting or something else to describe that system. So this is how UML plugs into a use case. Right now we're not talking about use cases so much, just UML. So here we have a class diagram, and I kind of showed you this in star UML. Like we said earlier, the top part is the class name, the middle part is the attributes, and the lower part is the operations or behaviors, right? And you can see that there's other connection types that we're going to talk about later on. So this is the class diagram. It's a main building block of object-oriented modeling, which we've talked about kind of last week. And those are the three parts we talked about. So all that information is here to reference later on. And again, we also talked about set accessors and get mutators and what those things would look like and what they mean. This is important. And now this modeling program, I didn't see where it said derived as an example. But normally you can do a plus, usually represents public member variables or methods. So again, member variables would be attributes, methods would be operations, right? A minus sign means private, protected is a hashtag, and a package, we'll talk about that, which is like a module, is a little tilde. And static is usually underlined. And usually what we use static members for are things that you want to use without instantiating an object. We can also use them so that all objects share the same maybe attribute or something. We'll talk about that later on if you don't know what that is. Member scope. Again, what we want to talk about is there are two scopes for members. Classifiers. So example, is it static? Or instances. As an example, as instance members, right? Objects, if you will. Okay, so those are two types of scopes for members. Keep in mind that classes are really a template for creating objects, and signals are symbols that represent one-way asynchronous communication between active objects. Almost like I want to send a message to another object. Messaging is what we're talking. Events are an example of signals. So if I want to have like a click event on a web page or something like that, or a click event on a menu system, or a touch event on a mobile game, or a swipe event on some mobile device, all those things are examples of signals. Okay, interactions. You're going to see different kinds of, and this is, I'm sorry about the resolution of these. There's a dependency, there's an association, a generalization, and a realization. And you're going to be like, okay, what do all these mean, Tom? The ones we really care about are generalizations, which is kind of depicts the inheritance relationship, which we just talked about. So remember, the inheritance relationships mean that the class that I'm coming from and the class that I'm pointing to, the class that I'm coming from is the subclass or child class or derived class. Remember, we have all the same kind of words to depict those things. So again, in our star UML diagram, the subclass or child class or derived class, all the same meaning, by the way, for the most part, they point to the superclass or parent class or base class. Those are all the same words that mean very similar things. So that's what this symbol means. This arrow is what we're going to be very familiar with when we do UML diagrams. Okay, so that's what this is. And we also have associations. There's different kinds. One of them, the one we care about, has a different end to it. It's a composition. can anyone remember, and I'm talking about composition, programmers out there, lead software engineers, tell me, can anyone on chat tell me what composition is with respect to object-oriented programming as opposed to inheritance? Very short, 2 seconds. Can you tell me what composition means? You may not know that word, but okay, has a instead of is a. Awesome, Kyle. That's great. Okay, what else? What other ways can we talk about composition? Is there another way someone can talk about it? How about an example of a class using composition, right? And there's a common example that we should all be able to tap into. Part of a thing. Composition is when a class is a member that is another class, while inheritance is when a class is a child of another class. Yes, that's a pretty good way of thinking about it, Roderick. Let's think of it like this. Here's a great example of composition. I want to make a transform component. My transform component, right, it has a few things inside of it. I'm creating almost like a new data type in some ways, right? One of the components of my, data members of my transform component might be a position. Another one might be rotation. Another one might be scale. Those components, they could be a single variable, but it doesn't make sense. Those components are also probably vectors of some kind. So for example, I might have a position vector, a scale vector, and a rotational vector, right? So all those three components, they're composed of a more complex class called vector, whether it's vector 2, vector 3, vector 4, whatever, okay? So that's an example of composition. And then let's take it further. I have a transform and I plug it into a game object. My game object doesn't inherit from my transform. My game object has a transform component. And my transform component has a position vector, has a rotation vector, has a scale vector, and so on. So that's a great example for you guys to remember in terms of composition. And why is it better than inheritance? In some ways, if we can compose our classes as opposed to inherit from other classes, we create a different type of coupling than a dependency chain. Because what's happening is when we have this hierarchy, one class depends on another class, depends on another class. And like I said perhaps last week, is the child classes, and here's an example. Let's look at that star UML diagram again. The classes are fatter, the child classes are fatter than their parents, right? Which means from a memory footprint perspective, they're bigger. They have more stuff in them, right? Inheritance means that the student has everything that the person has, and then some. It also has studies, which is a method that this person does not have, as well as the student ID property, which the person does not have, right? So because the student has more than the person class, therefore the student class we can say is bigger, fatter, bigger memory footprint, what have you. And this hierarchy chain, like we talked about before, just to reiterate those things we talked about last week, creates an inheritance problem. If we have a lot of classes, one inheriting from the other, we create objects at the bottom that are very massive. They're big. And it creates, especially if you use something like a game object that inherits from something else, and so on, it's bad. However, composition, although the classes can get fatter as well, we can stop the inheritance chain a lot earlier. We don't have to inherit, from transform to make an object, right? A game object. We don't have to do that. And we can plug in any of the components we want. Hence the idea of an ECS, an entity component system. All right, so let's continue. So that's some of these symbols we need to know about. And I apologize about the printer. Somebody decided to print now, especially when I'm teaching. It's awesome. So again, we can think of what the system must do to how the system will do it. That's really why we want to use UML. And one thing that's awesome about UML is we can do auto-generated code from some of the more advanced UML applications out there. And why is that awesome? Because that means that I can get going with, by using UML. All right, so we can model our code. We don't have to write any code, and it'll scaffold out or create almost like stubs of all the methods or classes that we want to create. And what this will do for us, it'll help us code quicker. than if we were doing things by hand. Some people are against that because they're like, wait, one day the computers will take over the world and I can just press 2 buttons or dictate to Siri and they're going to code for me. Yes, maybe to some degree, but it means that we're going to have other opportunities to work in different ways. So don't let that deter you. So here at a very high level are all the different kinds of relationships that we have in UML. Now, I got to warn you that I'm not going to expect you to memorize very many of these because we're only going to have a chance to use some of them. Hey, here's that composition one. Notice that the symbol is like this really weird, kind of triangle or diamond. That's pretty cool. We're probably going to use some of this, right? Hey, look, inheritance. This is important because we're going to use this general relationship kind of thing. We're going to see this generalization is something that we're going to be using a lot of. So these two you should know, right? Because it makes sense for us to know. And there's going to be other ones that we're going to be talking about in a second. Okay, but some of them in the beginning won't make much sense for you. All right, so go slow with UML. No one expects you, especially me, to learn everything there is to know about UML. Remember that you're trying to communicate the code that you're making, right? So lead software engineers out there, if you learn about UML and you talk about stuff, even to artists and designers, they'll get it. They can look at it. They can look at the code and go, without looking at code and go, yeah, I see what you're doing there, but wouldn't it be better if we had this? Where's that? They could actually, kind of add to the conversation in some ways, where normally when they look at code, they're like, I'm lost. I have no idea what that means, or I don't understand your structure, If you're making a game engine, this becomes even super more important because your game engine is your code and it's your own. And a lot of us don't like to do documentation, like I said. All right, here's the activity that I talked about before. So using star UML in pairs or alone. I'm okay with doing it alone. Actually, I said in alone up online. Let's do it alone. All right, so instead of UML, let's say alone, because I think it's good practice for everyone to do, right? Working alone, okay? Create examples of your own associated to your game idea, and this should take no more than 15 minutes. I'm going to pause the video here while we do this little exercise because I want to help out. Actually, I'm just looking at the time. I don't have time to pause the video to do this because I'm going to time out, and this is the difference between us being remote and us being together in class. I'm going to keep going, but what I want you to do is while I'm talking about stuff, right, and I'm not going to go too fast, I'm still going to be talking about UML, start thinking about what that class is going to look like. Start small. It doesn't have to be your entire game idea. Start with something like a game object. If you're going to code a game engine on your own from scratch, what would your game objects look like? Would you have an actor class? Would you have a class that's rendered? Or a class that is, as an example, would there be a game object that isn't drawn of in some way? So again, remember, you should know that there's 3 types of game objects that you should have access to. So one type of game object is only drawn but not updated, right? I'm just giving you some hints on this one. Another type of game object might be updated but not drawn. And the third type of game object might be updated and drawn. Can we get examples of those from the chat? So give me an example of a game object that is updated but not drawn. Can anyone give me that example? A manager class, okay. But is that a game object though? Could be, but that might be a class, but not a game object. A bounding box, awesome. How about this? How about a checkpoint, right? Or a spawn point. Okay, UI canvas, that's fine. Anything like that where some kind of a boundary that you're going to cross or a trigger, that would be a game object it's a game object in the game, but it's not drawn. Let's think about a game object that's drawn but not updated. Can anyone think of those? That's really easy. A game object that's drawn but not updated. All right. Skybox, awesome. Background, yeah, we got it, guys. And what about the other game objects? Obviously, we know drawn and updated would be an actor, an enemy. So we could actually think about this as a base. Think about this as a game object that is the base class or abstract class. You're not going to make an object of type game object necessarily. Maybe you're going to make an object of type actor or of type display object, as an example. Display object, if we're going to go in that direction, would inherit from the game object superclass. The game object itself is not drawable, let's say, at the beginning, right? And you might have some other kind of object, one that is not displayed. So think about what that would be called. And this is what I'd like you to start thinking about when you make your diagram. There's some examples here also online that have been included from the past. I think it's good to look at those as well. Okay, guys, I'm not looking at a big example. Let's think about, a simple diagram that is fairly complete. So if I'm going to look at a game object or something like that, think about what all the other types of game objects are going to be. All right, it doesn't have to be very long. Heck, if you just make a couple of classes, I'll be so happy that you've done that. If you submit it on your in-class exercise, it does two things for me: get you to practice, and I get to know, how detailed you are. By the way, if you don't want to finish this in class, I'm giving you until tomorrow night at midnight to really make this nice for yourself and to practice. Okay, so you don't have to do it right now. Okay, so I'm going to continue while some of you might be working on that, and I'm just going to talk. And you might want to be able to put this on one part of your screen if you want. As an example, I'm not going to go too crazy. Let's see what's happening here. If I was going to look at the UML diagram, not that we've talked about UML diagrams a little bit, right? Okay, let's look and see what this means. I have a customer class on the top left, okay, as an example, and I see that I have an order class on the right. I have these numbers here, 1, and I have this 0 ... star, okay? So that means something. The little numbers there mean something. I also have this up here, okay, which looks like a generalization, and here we have associations. So an association, then, a customer and an order, they're not depending on each other, right? I don't need an order to have a customer. I might have an order for a customer, or I might have no orders. Notice that you can see that in the association that we've created here, that in this case, it's 0 to many. Star means many, right? 0 to many. So I can have 0 orders or more than 1 order. That's what that means. But I must have 1 customer for every order, right? Therefore, an order is associated with a customer and perhaps has a dependency that the customer must exist, or else an order cannot be alive. Let's continue. A payment, as an example, you see that there's also an association. It's a different kind of arrow. And you can see that for every order, there's 1 or more payments. I could have different payment types, perhaps. Maybe I want to offer up different payment types. Payment would be a superclass, right? An abstract superclass. You can see that. And we have, as an example, and notice an abstract superclass, by the way, has an italicized name. Okay, it's not a regular name like customer. Notice it's slightly italicized here, right? So payment is the superclass, an abstract superclass for credit, cash, or check. These are specific classes, and the specificity, or how specialized these classes are, make them different. Even though all of them, you can say cash is a payment, credit is a payment, credit and cash are different. There's not a relationship between credit and cash. The only thing that they have in common is that payment is the abstract superclass. So that is this inheritance generalization. Okay. And we also have other kinds of things in here. An order detail, which is an aggregation. Normally there's 1 order, and we might have more than 1 level of detail we want to get into. For example, you could have 0 or more items in the order detail. Okay, so that's the way you would read this thing and how everything relates together. And there's, on the next page, it actually talks about these things. So the black diamond is composition. The simple aggregation looks like this. A generalization has that arrow, and you can see that this is another example of an old one. A DVD movie, a VHS movie, and a video game, they're all rental types in the old days. Nowadays, they're not so, it's not like you have a video store that you can go to and rent stuff. Back in the day, you could. And I think this is a pretty good example. All right, so that is the what's happening here graph. let's go into more details. Again, you can continue doing your little example while I'm talking. I'm just going to talk about certain things. An association, a broad term that encompasses just about any logical connection between one thing and the other. For example, an airplane and passengers. You must have, if the passengers are going on an airplane, they must be an airplane if they're using air travel, all right? But an airplane also has an association with passengers. Passengers and airplane, they don't depend on each other in this diagram, right? You can have an airplane that's empty of passengers, and you can have passengers that have nothing to do with an airplane, right? But in this case, you can see that passengers and the airplane are related in some way. A direct association says that a airplane depends on having passengers, and this is semantically weak because, as an example, in this case, we're saying that this association is it's not the same as us saying that airplane derives from passengers. This arrow here, which is a closed arrow, talks about a direct association, which means you must have we need passengers on the plane in this example. Again, it's a weak relationship because it may not always be true. Okay. A reflexive association is where we have 0 or more, right? Look what it says, 0 or more, and it kind of points back to itself. It occurs when a class may have multiple functions or responsibilities, and a person can have multiple roles in a company. An airline staff, there can be different kinds of airline staff, and so it's a reflexive association, right? Multiplicity is what we've been talking about. When I have 0 ... star, an airplane can have an association with 0 or more passengers. It makes sense, right? When you look at this, the numbers make sense now. So we have an association, but it's not a weak relationship anymore. It's a logical association that's using multiplicity. Okay, so this is where people get really confused. All right, an aggregation. All right, so a weak relationship and the associated objects are a crucial part of the containing object. So I need them. For example, I can't have a library without books. That's an aggregation. I have an aggregation of books that make up a library. I have an aggregation of cards to make up a deck, right? I'm playing Magic, and if I tell you I have a deck of cards playing Magic, I can't play with you if I have 0 cards in my deck, right? Do I really have a deck without cards? Maybe. You can maybe have the empty set, right? But it doesn't make any sense. That's why it's crucial that I have a deck of cards in my deck, right? Okay, or books in the library, this kind of thing. Okay, and you can have 1 or more. Notice that it doesn't start with 0. I can't have 0 books. Therefore, I really don't have a library with 0 books. I don't have a deck with less than 1 card, right? Composition is what we talked about before. It's similar to an aggregation. However, it's a key when it comes to, well, you know what? My library is made up of books. Books is the class, and my library is made up of it. So you can see that you can make this relationship as well. Different ways of describing the same kind of thing. One more specific maybe than the other. This one is, again, the most common one that we're going to see, which is inheritance or generalization. Okay. And realization. Okay, now this is people, when they first look at this, are like, what the heck does a realization mean compared to a generalization? And for you, it's almost like there's a system or a process, if you will, that creates or uses an object. So in my mind, I always think about, when I think about printer setup as a great example of realization. Is printer setup, could it be code? It could be. A driver would be a great example of a printer, a realization. I want to be able to activate the printer. I need to somehow set it up or create conditions where the printer can be used. That is a realization. If I can create conditions to implement my printer object, that makes sense for realization. A dependency. And this is the kind of stuff we want to avoid as much as possible. Let's suppose I have a dependent class, right? I have a dependent class method, and I want to, my derived class is going to use a method from a class that is dependent. Notice the arrow? That means I'm using a method, let's say method A, that's been defined in another class. A good example of that is using a static utility method from a manager class. Like example, I don't know, distance. I want to have a distance calculation from one object to another object, as an example, right? If I get the distance calculation from a utility math class, I have a dependency on the method that calculates the distance, right, from for me for two objects. Creating dependencies is typically a bad thing. All right. Why? Because now we've created tighter coupling between one class and another, right? A lot of times we want to make it so that it's independent, and we can plug in, kind of the methods from different classes. And we can see this later on when we talk about the factory design pattern. The factory design pattern creates a loose coupling, right, of, kind of a way of creating objects, right, by using almost a state machine to pick which object I'm going to create. And we're going to talk about that later on. So don't worry about that. But think about, in your mind, whenever you think about dependency, typically we don't want too many dependencies in a particular class. Sometimes we have no choice, right, when we create stuff, but we don't want them. The more dependencies we have in a class, if they're super dependent, that means they can break easily. If one dependency breaks, the entire class breaks. We don't want that to happen. All right, documentation. Okay, let's get a show of hands. Who is done their UML diagram? Can you give me a check mark if you're if you think you're done, right? I want to kind of go there. Okay, so I got Craig. Craig says he's done. Anyone else? Sorry, I'm calling out your names here on YouTube, but
3:15 p.m.
It's 3:15 p.m. That's right, and it's I want to make sure that you guys are done. So Anthony says he's almost done. For our game or of the same one we made? Sure, it could be the same one you made. If you followed me along and made a person class and and you did it, I'm totally fine. As an example. Again, this is just all practice for you guys, right? I want you to be able to look at the tool, any tool. Star UML is just one of them, and understand how to create something. Kennedy says, pretty colors have been added. I like that. That's pretty awesome, right? I like pretty colors. Pretty colors make it more interesting to look at, especially from a design point of view. All right, so I'm just going to clear that up on the on our participant panel there. Thank you for that. So let's talk about documentation. So again, there's different kinds. One of them we talked about already is this user requirements specification, also called a BRD, or business requirement document. For each class, we must have some kind of business requirements. Why does that class exist? Why do we have it there? Also, we have for system requirements, and a system is usually more than one class, and it actually does something. A manager is a great example of a system, or an AI system is another great example. A physics system, right? Or you could have a physics engine that plugs into your game engine. That could also be described as a system. You might have something called a systems requirements specification, or a system requirements document, SRD, right? So these are the things that you may have. From a game and development standpoint, title, platform synopsis, mechanics, story, characters, players, audio-visual elements, all that kind of stuff should be into something called a game design document, which is something that's not really listed here. Let's talk flowcharts now. Again, if you wanted to, instead of doing a UML diagram, or if you wanted also, have a flowchart diagram, I'm not going to go too much more into this from a flowchart perspective as much as I did with UML. I'm going to leave that to Nicholas, that part, but I want you to think about this is another representation, or it could be, of an algorithm or even a class. Let's talk about this in a bit. So let's talk about ANSI ISO standard for some of the symbols you might see in a flowchart. Again, it's another way of communicating different things. So here we have an arrow. This is a flow line. Okay, that's what it's called. We have a rounded box like this, a pill, if you will, a pill box. What this is normally is a terminal. Okay. Process, some kind of process, is a rectangle. A decision, yes, no, is a diamond shape. Input and output is a parallelogram, right? And kind of this connection is an annotation, which you have some kind of comment that you want to put in there. Predefined process that you're following is like a process with two bars at the end, right? So it shows the name process, which is defined somewhere else. So for example, I might have another page for that process, separate page that defines it in a lot more detail. And so we go look at this page number 5 defines this process, and you kind of go into that process, or think about it as a subroutine, if you will, right? An odd page connector and an off page connector. Off page connector basically says, hey, go to the next page, right? Flowchart shapes. We also might have a data file or database, some kind of documents you access. These are added in to the process that you're defining, and manual input and preparation or initialization. Sometimes we have these things as well. So some kind of elongated hexagon is used. So why am I showing you this thing? Because it's an alternate way of describing information. So here's an example. It says a guide to understanding flowcharts. I love this one. So you start here. Notice that there is a decision, right? And then, do you understand flowcharts? Yes. Excellent. Good. Right? Yes. Notice that there is no way of coming back down here. This is a directed graph, if you will, right? So the flowchart tells you the way it's going to work. It connects with things that it can go to. Good doesn't really do much. It just goes, yes, there isn't only one option. It's going to continue flowing through. Let's go drink. Awesome. 6 drinks later, hey, I should try installing FreeBSD. Yay, if you like Linux. Okay, what about if you don't understand flowcharts? Okay, let's go down here. Okay, you see the line labeled yes? Let's say we don't see it. No. But you see the ones labeled no. Yes. Wait, what? Right? So you can see that this is how, a flowchart kind of basically directs the flow of your decisions a lot of times, or the flow of an algorithm. Flowchart. And these are flow lines. Okay, so that's what they're used for. We use flowcharts a lot more for things like, if I was going to describe a decision tree to you. Example, I have an AI. And when I teach our artificial intelligence, then I think about using things like behavioral diagrams, like a decision tree matrix. I want to go left or right. Usually the decision trees we talk about, there's 2 types. There's a decision tree and a behavior tree. The decision tree is like a flowchart, and basically it does something like this. It says, okay, do I have line of sight? Yes or no? Yes, I have line of sight. Am I close enough to the player to attack? Let's say I'm the enemy. Yes or no? If I'm close enough to the player to attack, then do a melee attack. Perform a melee attack. That's the end of that little line of artificial intelligence. Let's go back a step. I'm not close enough to the player to attack, but I do have line of sight, right? So no is the answer. Cool. Move towards the player. That's the next action. That will be the leaf action that I have for my AI. Okay, and then it would just reset. Am I close enough to the player to attack? Cool. Attack, right? How about this? I don't have line of sight. So I don't have line of sight. No. Fine. From there, if I don't have line of sight, as an example, is the player in my hearing radius? Can I hear the player? Let's say I'm playing a game where the enemies have a hearing radius or a detection radius of some sort, right? So he's in my radius. I know that they're in the room somewhere, but I can't see them. There's no line of sight. Cool. Move to line of sight, which means try and find the player. Search for the player, maybe. Might be another action. You can use a flowchart for this, where it's a simple yes and no, okay, to describe the tree. Okay, hopefully that helped you from an understanding perspective. So I'm not going to do this activity. This activity is for you to do on your own. So again, a lot of this stuff would be great if we were together, and I think we could probably make a flowchart, and I would have a second in-class exercise for you to do. However, what I will allow you to do is, if you haven't started your UML diagram and you'd like to make a flowchart instead, you can take that UML example as an example and think about behavior for that game object, or the thing that we just talked about. I want to make a simple AI, to attack the player. Maybe I want to make 2 types of loadouts. I want to make a loadout, an enemy object that can attack and do melee damage only. So I can only kind of do hack and slash kind of stuff, right? Or maybe even, some kind of blunt force damage or whatever, right? And I might have another type of enemy who's only ranged. There's only a ranged type of enemy. Maybe they cast spells at your player, or maybe they use some kind of a missile weapon of some kind, right? Where they use a bow or a gun, or something like that, right? So those are the 2 types of loadouts. Think about the flowchart when it comes to their decision making. And let's even go further. Let's say that the enemy that is a range type enemy, when they get hit, you can make a behavior for this. When they get hit, they pop behind cover, and when they wait a little bit of time, and then when they're done waiting a little bit of time, they pop out of cover. If they have line of sight, they fire at the player. If not, they're going to have to find the player again. Whereas the melee type of loadout, from an enemy perspective, may have to do a little bit more patrol and get close enough to the player, rush towards the player in order for them to attack, because they don't have a ranged weapon. You can do that with flowcharting, and it's really nice and simple. And you can describe the entire artificial intelligence from a decision matrix perspective. Very simple, of course, but you can do that with flowcharting. There's a couple of flowchart tools you can use that I've listed here. One of them is dia.installer.de. Dia, it's an actual German little tool that you can download. I'll let you go there. Microsoft Visio is probably one of the most popular flowcharting tools, and the one that I like a lot is draw.io, because it incorporates or works well with Google Drive. If you try this out, draw.io. So if I go to up online here and I go draw.io. So I've already done my authorization on Google Drive here, so I can sit there and say, okay, I want to create a new diagram, right? And I can decide what kind of diagram to create. For example, I want to make a map or a network, or I want to make software. Let's look at software, and you can see that there's different kinds of diagrams. Look, one of them almost looks like a UML diagram. Look, here's the class diagram, right? So there's one way of thinking about it. It's hard to see here up online, but if you actually look through, and you can actually decide what the back end looks like as well. Okay. I can also look at other kinds of flowcharts. You can see that there are different kind of flowcharts here as well. And let's look at one of these, doesn't matter, or a decision. Here's business. So this is another type of chart that it can make as well. So this is pretty cool, and it actually does UML. So that's another UML option for you. So whether you want to do UML here with draw.io, or let's say I want to do a flowchart, let's pick flowchart. And notice that there in this one, I don't know if you guys can see this, very, very small. Let's see if I can zoom in here a little bit so you guys can see it. You can see that this looks like there's columns here on this flowchart type, and this one looks like there's rows. Actually, the rows are what we call swim lanes, where every time I hop from one swim lane to another, I hop into a different process. It's kind of neat, right? So another way of thinking. Again, we're hitting flowcharts now from a very high level. So let's look at something that we're familiar with. Something like looks like this. So I want to do this kind of flowchart. I want to create, and it says me pick a folder or use the root. Let's just use the root. Who cares? Let's just make my root of my Google Drive, crazy. And if you look through here, I'm just going to go zoom back out to a normal state. I can zoom in. And you can see that it gives you some basic objects here in order for you to create stuff. And all the things that we talked about in our ISO ANSI standards for making flowchart objects are here. You can pull them away. They're very flexible. And it's really quick in order for you to make this little diagram. So if you wanted to make a diagram with draw.io, nowadays I think might be the best solution for you guys, and it's totally free. Okay, so draw.io if you want to make a flowchart. By the way, for your documentation, I may ask you to do a flowchart or pseudocode. A lot of times, flowchart might be easier for you to look at, and sometimes you can derive pseudocode from the flowchart or a flowchart from pseudocode. And we'll talk about that in a bit. How does this relate to a diagram, a class diagram? I think a class diagram is definitely a higher level, and this would really kind of describe your code or a process, if you will. This could also be used to describe a case. So a user, what do? They go to the website, okay? Do they see the button? Yes. Do they click it? Yes. Now they go here, and so on. And you can describe different things that might happen in a scenario, as an example. Okay. Let's get out of here. So that's UML and flowcharting. Let's talk briefly about pseudocode, all right? You can submit now if you want. Totally, Craig. You don't have to wait. So pseudocode is a really high-level way of describing code, and it doesn't relate specifically to one programming language or another. Again, it's another way of us communicating with each other. So I want to be able to communicate my code idea to you, right? And it doesn't matter what language we're using. It doesn't matter if I'm using C++ or C# or JavaScript or Python or whatever language you feel like adding in there. The idea behind my algorithm might be the exact same, right? Because I might implement it differently in C++ than I do, for example, in JavaScript or in Python or Lua, as an example. But the idea behind my algorithm stays the same, okay? So again, here could be, this is some code. So int main, and we see some, how would you write the pseudocode for this, right, as an example? Well, we're going to come back to this, right? How do I write pseudocode, first of all? Well, we have some pretty cool keywords we can use. So some of the most common keywords are things like they specify an action. So here's where I start. I think it's important. Start. This is the start of your pseudocode, okay? You could also put end. It's not listed here, but a lot of times we can put end at the end of the pseudocode, all right? Input. This is data retrieved from the user through typing or through an input device. A read or get. This is input used when reading data from a data file. I want to read from a data file. I want to print, display, or show. I want to show data to an output, a screen, or some kind of console, right? I want to compute, calculate, or determine. I can use those words to do something. Like I want to take an action, a behavior, right? I can set values, or I can initialize values to a certain thing. So example, I can initialize or set my name value. I can set my age value for the person class, right? I can increment or bump, or I can decrement an object, all right? So decrement, increment. So these are basic keywords we can use in pseudocode. Let's take a look at that example further down. There's also conditionals and iteration types. So if I want to do conditionals, I would say if and end if. Notice just like start and end, I would have if and end if. And you can use basic words, very wordy. By the way, I want to tell you this. This is a funny story. COBOL, right? The language COBOL is based off of the idea of pseudocode, believe it or not. It was made very wordy, and it was made for people who are non-developers at the beginning, so they could create banking applications, right? And now COBOL, which is a dead language, sort of, is still out there. And they're looking for people to program in COBOL because people don't know how to do it. And there's a demand for it because a lot of banking systems and even gas pumps still use COBOL out there, believe it or not. Anyways, so it's based on this kind of language, just this wordiness that we're talking about here. So if, else, conditionals. If you are happy, notice that this is a very high level way of talking, then do something. Smile. Smile would be an action or a function, right? You would obviously replace that with some kind of function call or maybe more code. Iteration. For and end for. All right, so for every month in a year, this is almost like a for each loop, if you will. For each month in a year, for every month in a year. Compute. Remember we used that compute word? Compute the number of days. How many days in every month in a year, as an example. We also have things like preconditions. Preconditions to me are like sentinel variables. Whenever I make a while loop, I have to have some kind of way of ending that while loop, or I might have an endless loop. So example, I might have a counter. Count is equal to 0. While count is greater than 0, or as an example, or let's say count is equal to 50. While count is greater than 0, do, right? So now I keep looping, right? And then maybe somewhere in there, I'm going to decrement count minus 1, count minus, count minus equal to 1, whatever you want to put in here, right? Decrement count. While population is less than the limit, and here limit would have been the precondition. While my population is less than limit, compute the population as population plus births minus deaths. Okay, so this is kind of example of a small algorithm to calculate the population. All right, and then end while. Keep doing that. All right, while population is less than the limit. All right, let's continue. Functions look like this. You have the function keyword. The function will be called clear monitor. Notice that it's not the way we normally look at a function. And we would use end function, right? So we pass in, pass out would be the return type. pass in would be a parameter. You might have more than one of these, right? And we can direct, this is what it does, direct the operating system to clear the monitor. This is the action that this function does, right? Again, very high level from a wording perspective, right? And then when we want to call the function, we just say call, colon, whatever the function's called, clear monitor. Pretty simple, right? Doesn't matter. It's language independent, guys. The idea here is the same. You don't need the syntax, and that's what pseudocode helps you do. Avoid syntax that might hold you to one specific language or another. Okay, back to that idea. So that thing, how would you write this in pseudocode, is what we were asking. Well, really, that is helping us compute Fibonacci numbers until 50. How do I compute Fibonacci numbers until 50? Well, here's an example of that. All right, so I have some integers, n, k, f1, f2, and f. If n is less than 2, return n. Cool. All right. Else, now we're going to flip things around until we figure out the next factorial, the next Fibonacci number. Remember the Fibonacci numbers, how they work? 1, 1, 2, 3, 5, 8, 13, and 21, and so on. And it does all that stuff, this stuff, kind of as it moves forward. So it adds the previous number to itself in order for it to get the next number. Okay, how would I write this in pseudocode? By the way, notice that what I'm doing here is a function main, right? And there is no function that I'm calling here. I'm using this and some kind of integer, as an example, to calculate. And I only have one looping structure in here that does all the calculations. So depending on what my number is, right? If, for example, I want 50, I would pass in 50 in there. So let's do this. So declare an integer variable called n. N is the number limit. All right. Declare an integer variable sum. Okay. F is the sum. This is valid. Declare an integer variable f1. F1 is the temporary storage. Right. This is where I said we swap things around. And then f2 is temporary storage. Assigning the variable declared above to values. Set our loop counter to 2. Cool. Set the sum to 0. Set f1 and f2 to 1. Well, this makes sense because now I'm seeing f1 and f2, we add 1 to 1, and now we ended up getting 2, right? At the bare, so we would say 1, 1, 2, 3, and so on. We start up 1, 1. Set n to 50. Okay, so now we've set the number, so this is where n is 50. Let's look through this code over here on the left. If 50 is 50 less than 2, no. So therefore we do the else, right? Else, so 50 is not less than 2. F1 is equal to F2 is equal to 1. So both F1 and F2 is 1. That's what this is saying up here. This is another way of doing it, right? F1 and F2 set to 1. For where K is equal to 2, we start at 2. That's the start position, right? So it says repeat n times, okay? How many times are we going to repeat? Sum is equal to F1 plus F2. We swap F2 and F1 as an example. We make them equal to each other. And then we say F1 is equal to sum. And so what this does is it keeps on adding over and over again the previous number until, and we return finally at the end the number that's left over. So we keep on adding the first number to the second number. We keep iterating here until K is equal to N, where K starts off at 2. So example, in the first loop, K would start at 2, N would be 50. Since K is less than 50, we're going to loop, right? And we start off with F. F is the thing we want to return, right? Think about F as the sum, which is what this is. So again, it's another way of doing it. Is this the best, clearest example of pseudocode? No, I've seen a lot better ones. But one of the things that you want to see is pseudocode is just a description of the algorithm without actually using syntax for a specific coding language. And what this does for us is it makes it so that we are language agnostic, as opposed to we're writing a piece of code and we're sharing it with somebody, an algorithm, and it specifically, it has nuances of the language. It has curly braces, or it has semicolons, or it has a bunch of stuff that maybe not works for every language, because not every language is C influenced. Example of that would be Python. Right? Python doesn't have curly braces, and Python doesn't have semicolons. Right? It doesn't have any of those things. Or some languages have semicolons, curly braces, but no semicolons. Swift is an example of that. Okay, questions around the stuff we've covered so far in this lesson. We're going to take a short break, and it'll give you a chance, if you haven't had a chance to do your UML diagram, or if you want to do a flowchart, or if you want to describe things with pseudocode, any one of those three things, you can practice, and you can hand it in for some bonus marks today. There's nothing for you to do. Try and do it today, guys. Don't put it off till tomorrow because you're going to forget, and the Dropbox up on Canvas is going to close, and you won't be able to get your free bonus marks. Okay, so I think this is a great opportunity for you to do it now. So we're going to do a short break. I know people need some coffee and that kind of thing, and they want to run across to Tim Hortons and do a bunch of stuff. Let's take I'm sorry to do this, 10-minute break. I know it's not going to be enough time for everything. And after 10 minutes, we'll come back and continue with game engines. All right, for now, I'm going to stop recording on YouTube, and I'm just going to pause this whole thing, and we'll come back in 10 minutes. And I'll also take questions from you guys before I go.